On September 26, 2022, a refrigerator-sized impactor from NASA's Double Asteroid Redirection Test, called DART, or D-A-R-T, successfully completed the first ever full-scale planetary defense test to protect Earth from a potential asteroid impact. I can't emphasize how important this is because out of all the space missions that we've done, we are finally doing something that will protect all life on Earth with this planetary defense system. The impact and debris was spectacularly captured by the Hubble Space Telescope that was developed and launched at a cost of $1.5 billion, and the James Webb Space Telescope with a cost of over $10 billion so far, as seen in these amazing images. But could amateur astronomers have captured that event with a telescope that only cost $2,000, like the Unistellar? The answer is yes. Up next, we have Dr. Frank Marchus. He is the founder, one of the founders of Unistellar. He's also an astronomer at SETI, you know, the Search for Extraterrestrial Intelligence. And he is live with us now from California. It's great to have you on, Frank. Thank you. You've been busy with the Citizen Science Project with Unistellar. And I saw briefly an email, some excitement about the DART mission. And what can you tell us about what's been going on?
Yeah, thank you, Scott. Yeah, it's been a very busy time for us at Unistellar and SETI Institute because we published last week a paper in Nature describing the result of the analysis of observation collected by the Unistellar Network of the DART and impact before and after as well. So I have a few slides that Ariel Grekowski, who works in my group, prepare, and I want to describe a bit more with some visuals what we did.
Great. So
in short, the DART impact happened in September 26, if I remember, at 2 a.m. In Europe. And this impact was visible from the southern tip of Africa. South Africa, Namibia, Réunion Islands, Seychelles, Madagascar. And so what we did, we mobilized our network of unistellar telescopes. I remind you that those are small telescopes. I normally have one behind me, but today, for some reasons, I don't have it. But you have one on the screen. Those are digital smart telescopes that are relatively easy to use and powerful. They work in cities, they work in the countryside. And so we mobilized our network, and we told our network about this event and asked some of our users to observe it live during the impact as well. So some of you may have seen the live show we did at SETI Institute for like 2.5 hours, where I invited scientists to work on the project, including the PI of the DART mission, Andy Cheng. We talk about the event and what they were expecting, and then we followed the impact as it was happening. And at the same time, from Réunion Island, close to Africa, one of our users, Patrice Sué, showed live the event, and we saw the impact. And I'm going to show you that and going to tell you a bit more about what we derived. So this is the Unistellar network that contributed to the observation of the NASA DART impact. So we have, in this paper, we have 9 professional scientists who participated to the analysis, mostly the one at Unistellar and the SETI Institute, plus some additional scientists from elsewhere. We have 31 citizen astronomers around the world from our network. So you can see we have contribution from every continent, in the US, in Europe, I mentioned Africa, Asia, Australia, New Zealand. So we combine those observations together to to understand really what we were observing. Let me just go full screen here. All right, so Suzanne Murabana and the team of the Traveling Telescope organized an outreach event during the impact. And this is some picture that they sent us shortly after. And they observed it live from Kenya with our telescope, with people around, and really to connect, to appreciate the importance of observing an event which is extremely rare. I mean, this is the first time humanity tried to divert an asteroid body. We have not done that yet. So that was very an interesting event to witness. And they managed to do it together with three other team. And this is a video of the observation collected by Bruno Payet from Réunion Island. So you can see Didymos on the right moving, and you see
wow.
the puff of the explosion.
Wow. God,
So
Frank,
that's
that is extraordinary. Really.
yeah, that's really
Congratulations. That's extraordinary.
frankly, I mean, people know me. I was speechless when we saw that. We saw
Yeah,
that
I'm
live,
sure.
and I was not expecting something that impressive. I knew something would
But look at
happen.
that, the diffuse
Yeah,
material blowing off there, and
the ejecta and the material going up. So
sure.
this tiny dot is not Dimorphos only. Is Didymos the primary, which is 400 kilometer diameter, and Dimorphos the moon, which is 100 kilometer, 100 meter. Sorry, I say that's meter, 400 meter, 400 meter. So this is a relatively small body impacted by a mission which has a relative velocity of 22,000 kilometers per hour. So we really try. This is an impact of a small body with another large asteroid, and you see the impact. You see already how impressive it was just by watching it. So we put together the observation. This is some snapshot of the observation, and you clearly see a change of brightness between the observation before and after the impact. Before the impact is 2311 UTC, and after the impact is the time that I cannot read because I have my window on it, but you can read on the top, on the middle. This is at the time of the impact, and then you see the ejecta here.
It's just incredible.
And how it basically spread around. But that's not all. In fact, we monitor later on over the 26 days after the impact, the evolution of Didymos, and we saw the brightening reduce slowly, and we also saw the creation of a tail, a new tail, tail appear. Very
Its tail is
faint.
like 10,000 kilometers long, something
Yes,
like that.
10,000 kilometer length. And this is a tail which is almost it's located in the opposite direction to the sun. So that's implied that those grains here of material is extremely small because they push by the solar wind, basically. That's the sun interaction that push these tiny grains of material produced by the ejecta. So those data.
I am really amazed, and so is our audience. You can see there's comments here in chat. I think everybody is blown away.
Yeah, and this is coming from observation with this 12 centimeter, 4.5 inch aperture telescope. I mean, the technology evolved so much that we are now able to see things like this with the detector we have and this technology. So that was very impressive. The impact was impressive. The aftermath of the impact was also impressive. And frankly, it took a lot of us by surprise. But
yes,
luckily, I just hired Ariel Grekowski, who is a cometary activity scientist. She has studied comets over the past 5 years with Dave Jewitt at UCLA. And she joined our group as a cometary specialist. So she basically quickly understood that what we have done here is to create a comet.
Right.
Right? So she could use all the knowledge she had about comets to derive meaningful information about this impact. I'm not gonna give you all the details because it's a scientific paper in Nature, but I'm gonna show you this. This is very cool because those are 3 observations from Réunion Island, close to Madagascar. We have multiple users over there. Réunion Island is an island which is part of France, the same way that Hawaii is part of the US. And that's where I'm from, by the way. So that's one of the reasons I'm really happy to see this scientific result coming from the country of my mother, which is kind of a personal success for me. This is something I really wanted to do. So you can see the increase in magnitude is 2.5 magnitude increase, factor of 8, 9 roughly in brightness shortly after the impact, and you can see the decrease as well over time. So this is the same diagram, but in this case, we observe for 27 days. So you see the contribution of people around the world, from the Seychelles, from the US, from Australia, Japan, Asia, etc. And you can see the slow decrease, linear decrease in magnitude of Dimorphos. So what happened here is that after the impact, we have probably a cocoon of material around Dimorphos, and then slowly these materials went back onto the asteroid, or got ejected by the interaction with the solar wind. So slowly it cleared out, basically, and that's what you see. It took 27 days for the asteroid to lose this cocoon of fragments around it.
Wow.
So combining...
This is so cool, Frank. I am it's startling to realize that, you can take a telescope as easy to use as the Unistellar is, but you are doing high level science with it. And those images are, my jaw just dropped when you showed those. I have not seen those images before. Frank and I occasionally email each other, but I had not looked at this data before, and so I am blown away. I really am.
Good. I'm glad to hear that you're blown away. I was as well, I will say. We made bets. That's also live in the show at the Institute about what will happen. And I was the most optimistic. I said we're gonna have an increase of factor of 2 in magnitude. Yeah. Right? Well, even my optimism got lower than what we were expecting. It's been an interesting time for us to get this data and to analyze them and to put together a coherent analysis as well. Because from those diagrams and so on, we basically confirmed the amount of energy that was transferred from the impact to the moon. And we have the same order in energy that what was calculated by the other team that published paper in the same Nature, at the same time. So we have the same result, in fact, using our small telescope that people got with the Likia or the Hubble Space Telescope, or the continuous observation of the transit. We derived that the efficiency of the deflection was higher than was expected. So what is important here is that we believe now that we have validated the kinetic impactor as a way to deflect an asteroid. So if some threat comes to us in the future, we know we can use this technology to deflect the asteroid. And this has been done using data coming from citizen astronomers.
To me, Frank, this is as important of, I think, any space mission that humanity's ever done. I'm not saying that as a kind of tongue-in-cheek kind of thing. This is something that quite possibly would save humanity and anything else above the ground. Okay.
Yeah.
In case of a large asteroid strike, and so while there's no guarantees, there was absolutely nothing in place. I mentioned it earlier in this show. Some of us might remember when the International Astronomical Union said that the minor planet Apophis would indeed strike the Earth at one point. I think
Yeah.
landing somewhere off the coast, I don't know how many miles off the coast of California. And they described the impact and how catastrophic it would be. And they said it's going to happen. And at that time, there was nothing in place, nothing we could do, okay, to prevent a strike. And so to see this happen is one of the great things of humanity to accomplish.
Yeah, planetary defense is truly it's an application of the astronomy to solve a problem that could have a huge consequences on the future of our civilization.
Yes.
So it's not only astronomy, there is more than that. It's
Much more.
beyond, it's basically a survival of a species, which is being tested by this kind of experiment. So I like the fact that we validated the kinetic impactor for multiple reasons. I mean, we have this idea of sending nuclear nukes to explode the asteroid and so on, but we have so many complications because just putting nuclear bombs into a rocket, it's already a problem, politically speaking. So here we have validated a technology to mitigate, to deflect an asteroid that will not need this complicated, politically speaking, technology. This is easier to do in a way.
Yes.
We will be able to launch a spacecraft to deflect an asteroid if we know well in advance if this impact will happen. So we also have some weird things. I'm not going to go through all of it because we have some interesting observations, like we have seen a reddening. And we saw that live too. In fact, with the Unistellar Network, you can see colors, as you probably know, because we have a detector, which is a color sensitive detector. So during the live, suddenly we saw this color changed after the impact. The asteroid became redder. We don't know why this is coming from. If it's coming from the dust itself, some kind of geometry, or if we have excavated the interior of the asteroid and reveal the true color of the asteroid, which is redder than the surface. So that's what this diagram shows. Basically, and the line is the time of the impact, and the curve showed the difference of color B minus G, blue and green, or blue and red. So I'm not going through the detail of that because we don't have an explanation yet, but that's an interesting thing which we need to understand. Right now, we don't have yet an explanation. And I would like to mention that we are the only group who published the result of the impact live. Hubble Space Telescope missed it. JWST missed it. We succeeded in observing it.
That's awesome.
And the reason is because we have a network of people, citizen astronomers, motivated enough to stay until 3, 4 a.m. to do these observations.
Sure.
There will be always, I always said there will be always a starry night in the Unistellar Network. There will be always someone observing if something happening in the sky. And that's a clear validation of the fact that we have telescopes everywhere now.
And this is something sorely needed by the professional community as well, right?
Yeah. It's that's the reason SETI Institute partnered with Unistellar. We knew that this network has a huge potential to be able to observe any part of the sky at any time. So I want to mention some of the people who contributed to this because, I mean, as I mentioned, those citizen astronomers, they stay awake until 3, 4 a.m. to observe. They send us the data. They help us as well doing the analysis because we often need some information from them. So Patrice Huet from Réunion Island, this is what he mentioned, the feeling he had after he observed this emotional moment for him. And this is Réunion Island. In the background, you see the Piton de la Fournaise, which is an active volcano over there. So we have also Patrick Huth. He's a community college instructor. He's one of we have a program at SETI Institute where we deliver a unistellar telescope to community colleges, and we train the teachers, the instructor, to use them with their students. So Patrick Earth is one of them, and he has been using his telescope with his students, and he observed the Dimorphos and the after the dark impact in his classroom. And this is Ian Svenson from New Zealand, who also contributed significantly to these observations. Darren Rivet from Australia, who has observed as well from his I forgot the name of the city, but in his southern Queensland in Australia. So yeah, we have this network of people motivated to observe the dark sky and to do observations, to enjoy observing those galaxies and nebulae and comets, but also to do meaningful science. And now I want to emphasize that we are not only using the data of people at the Unistellar Network, we are involving them into the data analysis and their co-author as well. So those researchers, those citizen astronomers are co-author of the Nature paper, and some of them are extremely proud to be part of such an amazing scientific adventure.
Absolutely, absolutely.
And that's all I wanted to say. I mean, I could talk forever about that. But,
Frank, I do want to say something here. You know, there are, I know that there have been advanced amateur astronomers that did not give enough credibility. And I'm guilty of this myself, to the Unistellar Telescope. Okay, I'm going, oh, it's only 4.5 inches and it's this and it's that. However, I will tell you that seeing this data, okay, and knowing that this is something that that you could do on, you know, occultations, on comet outbursts, on this amazing DART mission, okay, it's historic, and it is, you know, it puts this telescope, I think, as a forefront tool to people who actually really want to do science, because scientists need the equipment to almost be invisible. They need to concentrate on the moment, okay? They need to be there. And the Unistellar lets them do this, okay? And so that is incredibly important. And, you know, many people, they own many, you know, maybe tens of thousands of dollars worth of gear. But rarely do they do science with such an instrument. This thing allows you to throw it in a backpack, go to anywhere at a moment's notice, okay, and get data, you know, and that is very important. And being able to join a global science team, you know, led by, you know, Frank and the people at SETI, I think is just nothing short of breathtaking and amazing. It's brilliant. And, you know, I'm definitely one of the converted.
Thank you, Scott. Wow.
That's the truth.
I hope we're recording this.
I'm not trying to sell it here, but I will tell you, I'm just dumbstruck by the results. I mean, it's just incredible. So, well, thank you. Thanks for coming on too. I know that you've been extremely busy, and you know, you didn't have much notice for tonight, but it's really amazing. And so, anyways, I'll let you go. But
thank you very much. Thank you, everybody.
Again. Thanks again.
Bye.
All right.
Thank
so.
you.